So I want to make sure that we focus our time, because we may not have time to go through the entirety of this practice test. And also, this practice test may not cover everything that you want to cover if there's a particular topic or something. So please feel free to let me know if you have any questions that's not on this practice test, and I'm happy to go through that. Plus, if there's any question on here or a topic that you want to just go ahead and skip over, we can go ahead and skip over it. So first things first, do you want to skip over number 1 with the naming? Are you comfortable with naming alkanes? Shall we just kind of skip that? What do you think? Or should we just go through it? And you can type in the chat or speak directly. I'm totally fine if you want to speak, to turn on your microphone. I actually prefer it because it makes it a little bit more active. But what do you think? Skip number 1, or should we go over it?
Skip it. I feel like that we can figure out.
Okay. Now, the next one, it says draw and name 3 compounds that are structural isomers of C5H12. And this one's pretty simple. I'm actually going to amp this up. Make it a little bit harder. And the reason I want to do that is because it will be more fun. Plus, it'll give you more of an idea of what you need to do when approaching problems like this. So let's say you have, draw and name all of the compounds that are structural isomers of C6H14. When you're dealing with structural isomers, what's the definition of structural isomer? Who can tell me that?
You have the same formula, but you're connected in different ways.
Exactly. They're connected in different ways. So with trying to figure out all the possible structural isomers, the first thing you want to do is draw the longest straight chain hydrocarbon. So in this case, that would mean 6. 1, 2, 3, 4, 5, 6. So here's a 6-carbon hydrocarbon. This is just a line structure. I'm doing that to kind of save time or whatever. But yeah, each one of these ends and each one of these corners represents a carbon. The next thing is, I obviously can't rearrange this in any way where I keep a 6-carbon chain but move groups around. So then I go to my next longest one, which would be a 5-carbon chain. 1, 2, 3, 4, 5. Now at this point, I have one more carbon that I can use to put a branch on somewhere. And I have a couple different positions that I can choose. I could put the branch here, and that would give me 2-methylpentane. What's another possibility if my longest carbon chain is 5? Where else could I put it?
Center molecule.
The center atom, the center carbon atom. Is there any other possibilities that would give me a new compound? What do you think?
I don't think so, because if you move it to any other space, you've already made that.
Yeah, if you move it to here, it would still be 2-methylpentane. And that's actually one of the ways in which you can definitively tell if something is in fact a structural isomer. If it has the same name, it's not a structural isomer. It has to have a definitively different name, particularly with regards to the number. Okay. So then the next thing is, if that's all I can do with my 5-carbon chain, then I go to 4 carbons. So 1, 2, 3, 4. At this point, I have 2 carbons. Now, because I have 2 carbons to place as branches, I could either place them as 2 1-carbon branches, or I could try to do a 2-carbon branch. But what happens if I place a 2-carbon branch? Does that give me a new isomer? What do you think?
Don't you lose a hydrogen?
No, you don't lose a hydrogen.
It looks similar to the one that's next to it.
Yeah, it actually ends up being the same as the one next to it. If I do the 2-carbon branch, that actually turns the longest carbon chain actually into 5. So that's not going to be a viable option. So the only and doesn't matter where I put, and I also always can't put I can't put a branch on the end because that also lengthens the longest carbon chain. So I always have to put my branches in the middle. So it looks like I'm stuck putting maybe a 1 carbon branch here and a 1 carbon branch here. Is there any other way I could put 2 1 carbon branches on a 4 carbon chain?
What if you put a double bond somewhere?
If a double bond will reduce the number of hydrogens. So a double bond is not going to be what I want to do. That'll actually change the structure. Or do you mean put 2 1 carbon branches on the same carbon? Is that what you meant by double bond?
Yeah, it's like a 2,2 dimethyl. It's not a double bond, I guess. It's just
Yeah, no, it'd be 2 methyl. So 2,2 dimethyl butane. Yep. So these are your 5. These will be 5 isomers of C6H14. But now you see how you can approach a problem like that. I do want to get into drawing Newman projections because that's something that, generally speaking, students have more trouble with. Does that sound good to you? Is that something you'd all like to go over? Newman projections?
Yeah, let's do those.
please.
Okay. So the easiest thing with drawing Newman projections for me, I found, is to go ahead and first write the carbon skeleton of the compound we're dealing with, 2,2-dimethyl pentane. So I'll write a 5 carbon chain because it's pentane. So C, 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 and C. And then it says 2,2-dimethyl, so that means on carbon number 2, I'll put a methyl on top and a methyl on bottom, 2,2-dimethyl. Now, once I have that, I can fill up the appropriate hydrogens. So I can do CH3 here. Now, carbon always has 4 bonds. So in the case of this carbon, I have 1 bond shown, which means I need 3 bonds to hydrogen. With this carbon, I have 4 bonds shown. I already have 4 bonds to carbon, which means I need no hydrogens. This one's going to need 3. This one's going to need 2. Now, I'll put it on top and bottom here for reasons you're going to see in just a moment. CH2, CH3. And this has down the C2c3 bond. Now the thing here with this C2c3 bond, so here's my carbon number 2, here's my carbon number 3, okay? Since I want to see all bonds to those carbons, all bonds to carbon 2 and all bonds to carbon 3. So there's 4 bonds around carbon 2, 4 bonds shown around carbon 3. And the reason I want to do this is because you're sighting down the 2-3 bond, which means the 2 is your front and your 3 is your back. Okay? So I'm going to circle the groups around carbon 2. I have 1, 2, 3 groups around carbon 2. That's my front carbon. And so remember, when we have our Newman projections, there's a circle representing the back carbon and there's a dot in the front representing the front carbon. The front carbon has 3. The front carbon has 3 groups around it. And the back carbon has 3 groups around it. Now you can have a staggered formation or an eclipsed formation. Which is more stable, a staggered or an eclipsed?
Staggered?
Staggered. So I know that my most stable conformation is going to have to be staggered. So I'll put my little back bonds staggered from the front ones. So now the 3 things attached to the front carbon, the C2 carbon, are the CH3, a CH3, and a CH3. So I'll go ahead and write that down. My front carbon has CH3, CH3, and a CH3. And then my back carbon, my C3, has two H's. Well, actually color those in a different color. What color do I want to use? Orange, why not? Okay. So here's my back. My back carbon, my C3, has an ethyl group and two hydrogens. So for that, I'm going to put two hydrogens and an ethyl group. CH2, 3, CH2. And you might be wondering why I put the CH3 on the outside and the CH2 on the inside. Well, that's just because the carbon that, where it's connected to carbon 3, remember that big circle is carbon 3. Carbon 3 is connected to a CH2, which is connected to a CH3. Because I'm moving outwards this way, I had to write it like that. It would be incorrect to put CH3 on the inside. Okay. So now, in this case, this problem is actually pretty easy because the fact that the front carbon has three identical groups, as long as it's staggered, the most stable conformation is going to be this. However, if you were to, for example, cite down the 3,4 bond, and I'll give an alternate example of that. So if I was to say cite down the 3,4 bond, then I'd be looking at this one and this one. Now the C3, let's say, would be the front carbon. And the C4, if that was the back carbon. So the C3 would be attached once again to, if this is the front and this is the back, the C3 is attached to a hydrogen, and then this tert-butyl group, and then another hydrogen. So hydrogen, and then a C, you can also write it like this, a tert-butyl group, CCH3, 3. So there's three CH3 groups attached to it. And the other side is the hydrogen. And the back carbon is down the 3,4 bond. And that's the case, we'd be looking at, I mean, this is your 3C4 bond. This would be number 4. So what's that attached to? It's attached to two hydrogens and a methyl group on this side. So for this one, I could say, okay, well, you know, it's a hydrogen, and a methyl group. Now, because all of the groups on this all the groups here are not the same. You have in the back there's a methyl group and two hydrogens. In the front there's a tert-butyl group and two hydrogens. You always want to make the largest groups as far away from each other as possible. So let me repeat that. With the most stable Newman projection, the largest groups, you want them to be as far away from each other as possible. So what I would do here to make this the most stable conformation is I would rotate the back carbon, or you could also rotate the front, but I'd rotate the back carbon, and basically I'm going to move this one, rotate this 120 degrees to put that there, which would rotate this 120 degrees to put that there, which would rotate the hydrogen 120 degrees to put that here. And then what that would look like basically is that the CH3 would be on top here. And the CH3 would be on top here. And the hydrogen would have moved over here. Now this would be the most stable conformation of the 2,2-dimethylpentane. Does that make sense?
Totally.
So this was actually the answer to that question. This is just showing you what the most stable conformation around the 3,4 bond would be. Just so you have an example of both. So you wouldn't just necessarily write a staggered conformation in the test and be like, oh yeah, that's the best one. And like, no, not really. Do y'all have Ayers? Do y'all have Professor Ayers?
No, I don't. I'm at the
Oh.
Northeast campus.
Okay.
Yeah, and I
How
think
about-
most of us are Gilchrist.
Oh, you have Professor Gilchrist. Okay. So I know that Ayers likes to throw multiple choice questions out and says which one is the most stable conformation of X. And it's actually a tricky one. You have to really look at it because you want as many of the larger groups as possible to be opposite to one another. And to the point where you can start counting gauche and anti interactions. When they're opposite to each other, that's called anti. When they're next to each other, that's gauche. So you want to minimize the gauche interactions and maximize the anti-interactions as far as possible. Referring, of course, to the larger atoms. I mean, hydrogen is fine if they're next to each other. We don't care about that. All right. So let's take a look at the next one. These chair conformations also tend to give students a lot of problems. Let's draw the chair conformation of cis-1-isopropyl 2-methyl cyclohexane in its most stable conformation. So in this case, first of all, we want to start with drawing our chair. Now there's lots of different ways to draw a chair. My professor would always actually draw them like this. Something like that. It basically looked like a lounge chair, an easy chair, so to speak. I know most of y'all's professors probably prefer you to draw it a little bit more like this. Like a sideways lightning bolt. However you want to draw it is fine. But the point is chair conformation. So the first thing you need to recognize with chair conformation is that, this is with cyclohexane. So you can really start anywhere you want. Anywhere you want to put the 1, put the 1. If anywhere you want to put the 2, put the 2. In this case, like my personal preference is generally speaking to start with the 1 in the top right position. So like maybe like this will be your 1 and this will be your 2 for this atom here, this atom here. Of course, then you have 3, 4, 5, and 6. Okay, now one thing that's very important, your axial position switches between up and down, okay? Before you even just start drawing substituents here, you should really identify your axial and your equatorial positions. So I'm actually going to color them differently just to make them stand out a bit. So I'm going to use purple for my axial. So axial, in this case, axial always goes in the direction that it's pointing with this type of a chair. So axial up, because this is pointing up, right? And then this is pointing down, so axial down. And here's your axial up, axial down, axial up, axial down. Axial alternates between up and down. Now, equatorial is always just out to the side. So I say, okay, well, this is equatorial to the side, equatorial to the side, equatorial to the side. I have to kind of, it's three-dimensional, so I have to kind of draw it slightly down, but it's directed off at an angle to the side. Whereas axial is always straight up or straight down. Equatorial, equatorial, and then axial to the side. Here we go. So, I should have Okay, sorry. I should have put those, tell you what, I'll highlight them instead. Okay, so I'll highlight my axial position. Axial, 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 axial. Okay, equatorial positions out to the side. Okay, good. Now in this case it says cis 1-isopropyl 2-methyl cyclohexane. Now cis means same side. Same side does not mean both axial. Same side does not mean both equatorial. Same side means either both up or both down relative to the other group that's attached to that carbon. So if I look at carbon number one, there's one group up and one group down. The equatorial is down, and the axial is up. Here, number two, axial is down, equatorial is up. And it switches like that, axial up, axial down, equatorial up, equatorial down. But if it's cis, that means they both have to be up or they both have to be down, okay? In this case, what would you like it to be? Do you want them both to be up or do you want them both to be down?
I think up is fine. It seems like it has more room.
Yeah, up. I mean, you can choose up. It's totally fine. In this case, so 1-isopropyl means that this is going to be a 3-carbon group, right? Carbon, carbon, carbon. Here's your isopropyl group, which means the other one is going to be a hydrogen, right? Because it doesn't mention, and normally a cyclohexane has 2 hydrogens on each carbon. So a substituent replaces one of those hydrogens with, you know, some sort of a group, like a carbon group. Isopropyl, there we go. And if that's up, that means the methyl group, number 2, is going to be over here. I'll actually write it as CH3. I probably should be consistent and just write it as a dot, but here, down here is a hydrogen. Now, the truth is, I really don't actually care about all these other hydrogens, so I could ignore the rest of this in terms of like whether it's the axial or equatorial, because I'm really only caring about these first two. Now, in what position is it more stable to have a larger group? In the axial position or in the equatorial position?
Equatorial.
Yeah, it turns out that the axial positions, these molecules or these atoms in axial position tend to interfere with one another. They have what's known as steric hindrance or steric repulsion. And the steric repulsion pushes these away from each other, and it's kind of high energy and they're not really crazy about it. So it's not actually super great that we have this isopropyl group in the up position. This would be the less stable. Now what we can do to draw the more stable stereoisomer is we can take this 2N here and we can rotate it up. And we can take this 5 corner here and rotate it down. So basically we bend the 2 up and we bend the 5 down. And if I do that, I'm going to get a different looking chair conformation. So I bent the 2 up. So let me actually label my relative positions here so you can see where everything went. So this carbon here is actually carbon number 2. Carbon number 2, the corner, that point, it bent from down to up. It bent up. So that's 2, which means that this is 3, which means that's 4. And 5 is now bent down. And then 6 is popping up here. And then number 1 is right here. So you'll notice here that what's also switched is axial and equatorial. My purple group. So axial for 1 is down, and equatorial is out to the side. Axial 2 is up. Equatorial is out to the side. And then, of course, the others, this would be axial down, axial up, axial down, etc. Okay. Why do we care? Well, it turns out that the relative up or down of this position hasn't changed. When you bend this up, the CH3 on carbon number 2 is still in the up position relative to the hydrogen. So that means the CH3 is now up here. And then the hydrogen, that means it's sticking out this way. On the other hand, the isopropyl group on carbon number 1 is still in the up position relative to its hydrogen. So that means you have the isopropyl group sticking out here laterally in the equatorial position, with your hydrogen being down in the axial position. And in truth, these two actually go back and forth between one another, but because isopropyl is so much larger than the methyl group, having the isopropyl group in the equatorial position is far more preferable, which means this is probably going to be like this some 85% or so of the time. The percentage, truthfully, is not that important. If it was 85 versus, 95. But the point is, the more stable configuration is going to be the one that is going to be the chair conformation that the molecule spends most of its time in. Most of its time is going to be in the right-hand side position, with only a small amount of time in the left-hand side position relatively. Does that make sense? In summary, up and down don't change. What changes is axial or equatorial. In both of these cases, the methyl group is up relative to the other group. In both of these cases, the isopropyl group is up relative to the other group. Cis means they're either both up or both down. Trans means one's up, one's down.
Is there other ways to draw this? Like if I drew it differently, is there other ways that you could draw it?
Yeah, absolutely. Would you like to, do you want to share what you drew, or?
Sure. The one, I don't know if you can see.
Okay, let me see. Let me try and pull that up on the main screen so I can get a closer look. Oh, okay, yeah, I see what you're sharing. Yeah, okay, and yes, that's totally fine.
Okay.
That's totally fine, yeah. You can draw it like that as well. Oh, wait, actually, show me that again. I actually think there may be a problem with that. Okay. Yeah, no, that's incorrect. Oh, wait, no, it is correct, because in this case, I chose to make them both up, but you chose to make them both down.
Okay.
But both would be cis. That you just flipped the molecule upside down. Both would be cis, so that is valid.
Okay.
That is valid. Mm-hmm. No worries on that. Excellent, excellent job. Okay. Next. Now, it says state how the two following compounds are related. Are they constitutional isomers, stereoisomers, or different conformations of the same compound? So what do y'all think? What would you suggest the first thing you should do to be?
Can we number them?
That would actually be the best thing to start with. Yes, absolutely. So let's number them. Let's number it according to how we would name it, just for consistency. And in that case, iso comes before methyl, right? I comes before M. Now it's tricky because technically speaking, if you terbutyl or sec-butyl, you'd actually go with the B. But iso, for whatever reason, that does get counted in alphabetical order, and this is an alphabetical order situation. It's the third level of priority of naming. So this would be number 1, this is number 2. Likewise, this is number 1, and this is number 2. So in this case, do you have the same groups attached to the same carbons?
Yes.
What do you think? Yes, you do. So you'd have the same groups attached to the same carbon, so it's not constitutional isomers. Now we have to check and see, do they have the same spatial arrangement? In other words, do they have the same cis-trans configuration?
No, one's cis and one's trans.
Absolutely, yeah. Because in this case, if you were to look at the other group attached to this isopropyl group is up relative to the other carbon, or relative to the hydrogen. And the other group, the methyl group, is down relative to the hydrogen. So this would be a trans 1,2 compound. But this one is clearly, they have them both represented as up relative to the other group, the hydrogen, which would be, in this form, it would be shown as like a dash to hydrogen. And likewise, this would be a dash to hydrogen. So yeah, the right one is cis, the left one is trans. And so in that case, they would be what?
Not the same. Stereoisomers.
They're stereoisomers. If they now the way that they would be different conformations of the same compound, how could you tell? Let's say if both of these were down and both of these were up, I mean maybe, but truthfully speaking, to be able to definitively say they're different conformations of the same compound, you would need comparisons like this. Like where it's still the same relative positions, like one up is one down, one's up and one's down, one's up and one's down, but they have different axial or equatorial arrangements. So that would be different conformations of the same compound. Just basically they're rotated a little bit differently, but they're still in the same relative positions. Okay. Now, unfortunately, it's asking for, did you do stereoisomers? Have you done that already?
Yes.
2R, 3S?
Yeah.
Okay.
Yeah.
So in this case, the easiest thing for to do with this is to go ahead and draw the root chain, like the 5-carbon chain. And so I do 1, 2, 3, 4, 5. And it says I have a 2-bromo. And I'm going to just draw it here. I'm not going to actually draw a wedge or dash yet. And I'm going to draw 3-chloro. Not going to draw a wedge or dash yet. And I'm going to I'll draw my hydrogen here. Hydrogen here. Now, the truth is I may probably just erase that hydrogen later on, but I like to draw the hydrogen just for emphasizing the different groups. So it's 2R3S. So after drawing this sort of skeletal structure where you don't indicate stereochemistry, now you need to indicate priority. So what's the highest priority group? And we're going to actually focus on carbon number 2 here. So I'm actually going to label it carbon number 2. Here's carbon number 2. What's the highest priority group attached to carbon number 2?
The bromine.
Yeah, the bromine's number 1. What's the next highest priority group?
This methyl group. No, the big part.
Attached, yeah.
Yeah, so it would be basically,
yeah,
this one down here. This is carbon number 2. And then the methyl group is carbon, this is 3, and then hydrogen's 4. Okay. Now, if we assume that hydrogen is in the back, okay. So let's say we assume that hydrogen, this is a dashed, hydrogen's in the back. What configuration would this have?
R.
It would have an R configuration because 1, 2, 3, that would make this clockwise, which basically means R. So I'll go ahead and erase that. It's going to be R, and we are going to have hydrogen in the back. Now, if hydrogen's in the back, that means we can put bromine in front. I'll simplify this by taking off the hydrogen and just drawing the bromine. And I know I need it in front, so I'll put a big wedge on it. Okay. So then I can go to, Then I can look at the next carbon, carbon number 3. Focus on this one. So what's the highest priority group here?
Chlorine.
The chlorine. And what's the next highest priority group?
Carbon attached to the bromine.
Mm-hmm. And the next one? The ethyl, right?
Yeah.
I figure you already knew that. And then the hydrogen. Okay, so in this case, obviously we ignore the hydrogen. We just look at the first 3. In what way is this rotating? Is it rotating clockwise or counterclockwise?
Clockwise.
So this would actually be an R configuration if hydrogen's in the back, right?
Mm-hmm.
But we want it to be. What do we?
2R3S.
We want it to be S. So if hydrogen's in the back, it's R. So the way to flip it to S is to, instead of having hydrogen in the back, we put hydrogen in the front, which means that chlorine is in the back. So I'll erase the hydrogen and I will put chlorine as a dash and put it in the front. And now I have 2R3S, 2-bromo, 3-chloropentane. Does that make sense?
Mm-hmm.
Any questions on that? Okay. Sometimes with these, if they get really complicated, like if you're asked to determine like what the, what it happens to be for a particularly complicated compound, one of the things that I'll sometimes do, and I'll show you an example using this molecule, but like, let's say we have this carbon here, okay, that red carbon. I'll write that as carbon here. And I'll say, okay, well, what are the 4 things bonded to that carbon? What are the 4 things directly bonded to it? And 1, 2, because carbon is 4 bonds, right? So, and what I'll oftentimes do as well is I will label the different carbons. So this is carbon 1, 2, 3, 4, and 5, right? So this carbon, the red carbon, that's carbon number 2. So I know that it is attached to a bromine. It's attached to carbon number 3. So I'll put C3. It's attached to a hydrogen. Oh, it's attached to carbon number 1. And it's attached to a hydrogen. Now I know that with the ones given here, this is already my highest priority group. That's number 1, right? And I know hydrogen's my lowest priority group. But as far as figuring out between 3 and 1, I mean, you guys figured it out pretty easily because it's relatively simple here. But in case where it'd be more complicated, where there's more branching, there's more extended chain, what you would do is you'd keep going. You'd go to the next level. So in the case of C1, carbon number 1 is only attached to hydrogen. So this would be a hydrogen, and and hydrogen. You list them in order of their weights. The higher weight go on top. Carbon number 3 is attached to a chlorine, a carbon, and hydrogen. So carbon number 3 is attached to the chlorine, which will go on top. A carbon, specifically carbon number 4, and a hydrogen. And of those two, it's the chlorine that wins out over the hydrogen. So therefore, I would be able to determine that this would be 1 for here, 2 here, 3 here, and 4 here. So C1 is basically 3. And this would be 2, and this would be 1. Does that make sense?
Yeah.
And like I said, you probably will not need to use that, generally speaking. You would only have to use that in the case of a really, really complex molecule. But I don't know what your professor might throw at you. Usually, Gilchrist is pretty straightforward. She doesn't usually throw too many curveballs. All right, what's next? What would you think about these? Identical, diastereomers, constitutional isomers. Sorry, I cut you off. Go ahead. What were you going to say?
They look identical.
Does it matter that the hydrogens are pointing in different directions when you put them along a double bond?
Yes, it does, because double bonds are actually rigid in the sense that they do not allow for rotation around the double bond, so they're kind of locked in place. They introduce a certain level of rigidity to the molecule. If the double bonds are locked on the same side, we call that cis. If it's locked on the opposite side, we call that trans. So what would that be then?
Diastereomers.
Diastereomers.
Yeah, diastereomers. It would be diastereomers. So, just out of curiosity, would y'all think, would it be helpful for me to kind of give a breakdown of the stereoisomers, like how to identify the different types? There's a flow chart that you can use to kind of determine where it lines up in terms of an enantiomer versus not an enantiomer versus diastereomer versus constitutional isomer.
Cool to see a flow chart.
Cool. All right, so I'll go ahead and I'll draw it. I think I'll go to the bottom because I think there's like a blank page at the end. Okay, so the first question you want to ask yourself is this. So do the atoms, or do the molecules you're comparing, 2 or more molecules, do the molecules have the same number of each type of atom? Question. So if the answer to that question is no, then they're not isomers at all. If it's yes, then you have another question. Well, actually, I'm going to be more fancy. Sorry, hold on just a second. Moderately more fancy. So if it's no, yes. Okay. So no. So add text button. They are not isomers. Not isomers of any kind. If yes, then you ask yourself, are they connected in the same way? In other words, do they have the same connectivity? Are all the atoms connected to the same atoms? Connectivity is the word, the fancy word we use in OChem to basically say that, are they connected in the same way? In other words, would the methyl groups be attached to carbon number 2 and 3 in both atoms? If they're not, if the methyl group for one is attached to carbon number 2, but the other one is attached to carbon number 3, in other words, if the answer is no, if they don't have the same connectivity, then that means they would be structural isomers or constitutional isomers. If the answer is yes, so then we have another question. So, constitutional, can't spell today, isomers. Constitutional isomers, otherwise known as structural isomers. Basically the same thing. If the answer is yes, then we have to ask ourselves, are the molecules mirror images of one another? And one of the ways you can tell if they're mirror images is they would have opposite RS configurations. So if one is R, the other is S. If one is RR, the other one would be SS. So they have to have the exact opposite configuration, opposite RS configuration to be mirror images. Okay. So if the answer to this question is yes, if the answer to this is no, if they're not mirror images of one another, but they have the same connectivity, then this is what we would call diastereomers. This is diastereomers. Okay. Now, if the answer is yes, then we have to ask ourselves one more question. Are they superimposable? And if the answer is yes, then we would say that they are meso. Or in other words, they're the same compound. The two are actually the same compound. If the answer is no, then they're enantiomers. Does that help?
Yeah.
So 5 possible choices. They can either be constitutional isomers if they don't have the same connectivity. If they have the same connectivity but are not mirror images, they're diastereomers. If they're same connectivity and mirror images, but they're not superimposable, they're enantiomers. If they are superimposable, then they're meso compounds, or they're the same compound. So those are your 5 possibilities when you're analyzing isomers. Cool. I'm kind of secretly proud, or not so secretly proud since I'm telling you of it, of my little flow chart here.
Yeah,
Okay.
that's super cool.
So what would you like to hit next? Should we just go in order?
Yeah, that works.
Okay. So it says this molecule has 2 chiral centers. Label each of them as R and S. So it's pretty obvious which ones are the chiral centers here. And you know how to easily tell if it's a chiral center, right?
Yeah.
Yeah, you just look for, see if it's bonded to 4 different things, exactly. So here is one chiral center, here's another one. What would the first one be? Is that an R or an S?
R.
Yeah. So yeah, this one is higher priority than this. By the way, what does a double bond represent? Like, how do you reconcile that? How would you represent that in terms of Cahn-Ingold pre-log notation? Essentially, how you determine priority.
I'm
Just
not
in
even
case-
sure I understood that question.
Yeah, I'm not
Well,
sure.
so let's say for example, I was doing this one. Okay, so here's your C, and it's attached to an oxygen, which is attached to a hydrogen, right? It's also attached to the benzene ring carbon, which I'll call CB. It's also attached to the carbon here, and it's also attached to a hydrogen, right? The carbon here is attached to the nitrogen. So this is the one on the right. It's attached to a nitrogen, carbon, and a hydrogen, right? But the benzene carbon, this one, is attached, double bonded to one, and single bonded to another. A double bond is treated as if it was 2 bonds to the same element, or 2 bonds to that element. So, in other words, this would be treated like C, C, C. So the bond from here to here is treated as 2 bonds, as if it was 2 separate single bonds. And that's how you order it in terms of Cahn-Ingold pre-log notation. So I just wanted to point that out, just in case it comes up and you have to deal with it. Okay. Let's go ahead and erase that since you don't need it. Blah, 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 blah. Okay. I probably wasn't asking that very clearly anyway. But anyway, so you got a priority. You say it's R, and you're absolutely right. So 1, 2, 3. This is higher priority. So this is going to be like this. And this is an R group. R configuration. What about the other one? This one. And the carbon right here. Got NH2, a methyl, and this thing over here. What's that going to give you?
S.
I'm sorry, what'd you say?
S.
S. Yes, very good. My apologies, I'm a little deaf. So, yeah, so this is just going to be RS. Pretty straightforward. Any questions on that? Okay. Now, both of these were wedged. If one of them was dashed, then we would have to switch it because the dash would mean that the hydrogen was out in front. And if the hydrogen's in lowest priority group is out in front, we have to flip the configuration. Now, what about these two? How are these related? This is a little bit more tricky. Any ideas?
Can you just find like the chirality centers for them and see if they're opposite, and if they're opposite, then they're enantiomers?
Absolutely, you can definitely do that. Now, of course, this OH is going to be number 1, and then this will be number 2, and this will be over here, number 3. So this looks like it's R. And the bottom one here, number 1, number 2, number 3. So it looks like S, except that it's wedged, I mean, rather that it's dashed, which means the hydrogen's in front. That's going to flip the configuration from an apparent S to an R. So this is RR. Likewise with this one looks like it would be R according to the same rules, but because it's wedged, it flips to S. This one looks like S, and it is S because the wedge is there. So this is an SS. So in this case, you can say that this is definite. These are definitively what?
Enantiomers.
Enantiomers. Another way you could test it, if you're good at like manipulating things 3D in your mind, if you flipped that second object here, if you flipped it over, like turned it over like a pancake, that top wedge group here would actually be wedged, or top dash group here would be wedged if you flipped it over like a pancake, and the bottom would be dashed, and they would actually be perfect mirror images of one another. Of course, if it had the key thing that you can tell that these would not be identical compounds, is like if you had both of these wedged and both of these dashed. If this was both of these wedged, it has an internal line of symmetry, which means it's not possible for it to have an enantiomer. And the ones that would be dashed, you could recognize that if you flipped it over like a pancake up and down, it would actually be the same molecule. But in this case, yeah, these are enantiomers. Here it says draw the enantiomer of the following compound. When drawing an enantiomer, the easiest thing to do is just to flip the wedge and the dash groups. The easiest thing to do is just to flip the wedge and the dash groups. So if I was to draw this enantiomer, there's actually a lot of different ways you could do it, but the easiest thing to do is draw the exact same thing in every single way, except when it comes to the wedge and the dash groups, I just switch them. This is my CH2, CH3, and this is my hydrogen. That's all I have to do. That's easier than what you were thinking, isn't it? Or were you thinking that? What were you thinking?
I like those. They seem straightforward.
Yeah, that's what I was thinking.
That's good. That's good. Yeah. Awesome. Awesome. Now this one says identify all the nucleophilic areas in the following compound. Now, what does it mean to be nucleophilic?
Sorry, Amanda, are we going to have those on our test? We didn't cover the nucleophiles, and I was just wondering.
I don't think that we're going to get into that part of chapter 6, so I don't know how she's going to modify the test.
Okay. Okay.
Sorry, I don't know if other people, I just was curious if there are. I don't know who's on here.
So,
We're on chapter 7 at the Northeast campus, but I really struggle with identifying the nucleophiles and
then definitely do.
Yeah, we're going to have to learn it anyways.
Yeah, so yeah, go ahead. Sorry, I was just curious.
oh, no worries. Nucleophilic areas are those, nucleophilic means nucleus loving. Nuclei are positive, right? It's the electrons that are around the nucleus that are negative. So nucleophiles are positive loving areas. So in this case, I'm looking for something that would be loving positivity. So basically something that would want to grab something positive. So the positive, so like for example, nucleophilic areas. So this nitrogen has a lone pair of electrons. This lone pair of electrons would be totally willing to grab something else. So this would be a nucleophilic. This would be a nucleophilic area. It would want to seek out positives. Likewise, because of resonance, keep in mind that anytime you have a lone pair that's next to a double bond, you can have resonance. So the resonance structure here, this nitrogen could donate its electrons and form a double bond here, which would break the double bond here and send those electrons up here. So basically, this would be a negative area here. So if you had, and that'll cause this to be positive here. So this is this could also be considered a nucleophilic area. Fortunately, we did get through all the stuff that most of you needed to cover. I am so sorry. I think we're going to have to cut out the nucleophile electrophile part. What I would, gosh. So let me just show you what I'd recommend. I'm going to offer something as a cop-out. Okay, my apologies. I go www.tcd.edu, academics. Here we go. And science support. If you go down to organic chemistry here, so under the video tutorial library, and you go down to substitution reactions, this will really help in terms of this. There's overviews of the different SN1 reactions, how it works, talks about kinetics and substrate, nucleophilic areas versus electrophilic areas, comparing nucleophiles and their strength.
Thank you so much. I'll check that part out.
Yeah, and there's also reactivity and mechanisms. So I'll let you go from there, but no, thank you for coming, and I hope that was helpful. I wish you all the best in your test. Okay.
Thank you.
Yeah, no worries. Also, where can we find this recording?
I will actually
out 3 times.
I will email it out to y'all. You'll be able to find it under Learning Workshop Video Archives. It's a button that I will add here under Organic Chemistry 1. So you'll notice that if I go back to the science support page, if I go to like general chemistry, you'll notice that you have Learning Workshop Video Archive. I don't really have any videos much for the OChem 1 stuff, so I haven't actually put that button on there, but I'm going to add that button. I'll add this video to make that available for you.
Awesome. Thank you.
Yeah, you're welcome. You can also check out my channel at the Casual Chemist on YouTube.
Sweet.
Okay, thank you.
Yeah, you're welcome. All right, catch you later. Thank you.